Guys, BBI here. I want to stop and say thanks for tuning in and checking out whatever the video is about that's about ready to come up next. If you could take a minute and hit subscribe, I greatly appreciate it. And if you enjoy what you've seen here, make sure to hit the like button. We'd greatly appreciate your support. Anyhow, guys, all that aside, let's get on with the show. You gotta go quick. I got a bunch of stuff going on this morning. Gentlemen, this is a worthmore. We're gonna go in here, we're gonna replace the power wires, of course. We've got our butt splice heaven going on here. So we're gonna see if we can salvage this Anderson connector. We're gonna delete the fuse, replace our power wires. Now, I will give credit where credit's due. First time in a long time where one of these came in and it actually had the right size clip for the job. So, we can tell that this thing's been repilled a couple times. If we look at the solder work, all of this has been hot many times up in here. It's just got an old school set of Toshibas in it. Yep, they're actual real transistors, not the Chinese knockoff ones. Anyhow, this whole area has been way too hot. So since the amplifier actually sits like this, we're going to go ahead and we're going to clean all the dirt out of the heatsink fins. We'll get that cleaned up a little bit. We're going to mount a fan on this, probably a little 120 millimeters, sit there and rotate nice and slow. And the other thing that we had happened is the pass-through. So as the RF comes in, it goes across the relay connection here. If you notice, there's some missing components here. There was a cap that's in here that helps pass the bypass tune through the box. Then it goes down, goes across, goes through another capacitor as a blocker, and then comes back out. Okay. We're going to replace this capacitor. It's gone. MIA. Not even any little fragments of it left inside the cabinet. The only thing we were able to find inside the cabinet was this little hunk of... Make it. There we go. This little hunk of shmoo. So, let's go ahead and let's do our dirty deed. We're going to pull both these transistors out and check them. The reason we're going to check them is because this discolorization here on this resistor. It leads me to the conclusion that possibly one of these two is toast. If that's the case, we're going to replace it with HGs and we're going to get on with the show. Now, the reason that this capacitor would fail would be excess amount of RF going through the amplifier. If we look down here at the input attenuation circuit, we got to take visual note that these resistors all have been very hot. Okay, so our input RF comes in here. All right, comes in here, down this trace here, and goes by this attenuation pack. This thing's been getting pushed really hard. So it is what it is. It's a 2-pill unit, and I mean, it's a worthmore. This is good stuff, guys. I'm not saying anything negative because this is. I like me worthmores. I got a couple of them sitting on the shelf that I personally own. Oh yeah, and we'll index your switch so it's straight up and down too. Okay. I got the phones are ringing like crazy today, so I need to get on to that. I just wanted to get the intro shot so you guys can see what we were getting into, so we can do a little bit of before and an after. We shall return. So, power wires are out, obviously, and rebuilt the jumper, and I pulled the transistors out, and the thermal compound that's on this heatsink is pink. Like gobbed with pink jizz. So I'm going to clean that off, and I'm going to clean off all the excess flux, if that's what this is. I'm not too sure. It's awfully soft. So that's flux over here. I don't know, unless it's like plumber's flux or something that they put on here. I don't know. We're going to clean all this off, clean all the pink shmoo out of here. I don't know what that is. And we'll test our transistors. I want to show you guys something real quick. It says in here desoldering all of this and cleaning this up. want us to look down at this transistor mount point, this hole in the heatsink, and these over here. We need to come back and chamfer these holes. The style of screw that they've used, which is this here, let's see if we can get this to balance on the screwdriver for video purposes here. No, the pink goo is going to get them here. Here we go. The style of screw that they've used has a tendency to ball the heat sink up. And I mean ball as in like engulling it. Look at all the flex I got on my hands. This thing's gross. It'll gall the heat sink and it'll cause it to curl up just like what we have here. If I was to go and lay another transistor down on top of this, it'd work for a few minutes, but once we get into heavy operation, that lifted edge of the heat sink, or that lifted edge of the transistor right there, would eventually cause this transistor to fail, because it would only be able to dissipate heat through that foot, because it's going to off kick the whole transistor. Instead of sitting flat, the transistor's sitting like this. So the only place it's going to make contact is on that outside edge of the ear. These are the things you guys got to have your eyes open for when you're doing a rebuilds and working on your own stuff. It's not just as simple as popping the transistors out and changing into other ones or putting new power wires in it. You got to be able to look at all the overall picture. So, okay, we got it defluxed, and now I'm going to go in there and I'm going to chamfer them holes out and get them all nice and beveled down and cleaned up. And we're going to go ahead and we're going to play with the output tune, or the pass-through tune, a little bit. See if we can figure out what value capacitor they had in here. I mean, in most situations that's more than appropriate, where it's just shorted directly across with a direct coupling to ground, but I want to see what it looks like across the whole spectrum from 0 through 30 megahertz and not just at some mono-banded frequency, if that makes any sense. So we shall return. See if I can get through this and not have the phone ring. So what we're looking at here is shown here by the frequency indicator. We're looking at 38 megahertz, 38.33 megahertz through 0.25 megahertz, which is almost infinitely low and well past what the transistor is actually rated to pass. Now what we've done is we've reinstalled a match set of HG2879s that was provided by the owner of the amp, and we've got this thing set in continuous loop. So it's generating a little bit of signal. It's going through the wire, coming down, going through this blocking capacitor, and it's coming through the blocking capacitor across, through the input of the relay, across the screwdriver. Now watch what happens. Take the screwdriver out of the way, put this back in. Now, we're not paying attention to the induction that this is actually adding. We want to make this loop that goes in and out of this box as low as possible. So RF's going across the connection of the screwdriver, going back down through the body of the relay, across the wire, out and around, and then through and into the dummy load. Okay? So what we want to do is we want to tune this with either induction and capacitance coupling to ground for the lowest possible SWR pass-through. So, put this on pause. The characteristics that are being displayed to us, yeah, it's the advantage of having a real piece of test equipment. The characteristics that this is displaying to us is that we've got a large amount of induction already present. But as we're going forward in frequency, as we're increasing or decreasing in frequency length, we are running low on capacitance. So, that's interesting. That's interesting. We'll come back to that in a minute. We're going to go ahead and we're going to short these two across, and we're going to directly couple back here to ground a capacitor. The idea is that we want to make the resistance of the RF going through the device as low as possible. That way the end user, i.e. you guys, have the ability to hear the best that you possibly can, and when the amplifier's off, it's not presenting itself as any part of a resistance that the auto-tuned radio that's going to be attached to this thing is going to see as something that has to tune around, which we can get a relatively low response. We want to bring this curve down to where it's almost perfectly flat, and that'll dramatically increase this guy's ability to hear. One of the reasons that it's here is because he told me that he was having a hard time hearing through the amplifier. Well, I totally believe that, taking into account there's nothing physically attaching these two tabs on the relay. It is schmuckgechucht. So, I'm going to take a wild guess. After a couple thousand of these, we're going to take a 30 puff capacitor. We're going to go across the two tabs and we're going to go to ground. And we're going to see what this does to the graph in comparison. So give me just a second. So we've added our 30 puff capacitor. We've officially tied these two legs of the relay together. And our 30 puff capacitor coupled to ground. We're going to be 30 to 50 puffs, somewhere in there. A little bit high, a little bit low. Just guessing on 30 puff. And we brought it down directly, coupled it to ground. Now the lead length on the capacitor makes a big difference. Sometimes it wants to have a little bit extra induction. Sometimes it wants to have a little less induction here or a little bit more. But let's see what we got. So here's our old graph, and let's see if we got any change. Poof. See that? So now we've cut our pass-through standing wave from a 3 down to a 1.5 on the high end. But if we take our track indicator, we scroll that around to 30 megahertz, we have a 1.15. See that? Now as we get down here, let's go to the other tick indicator that's over here in the corner. So we're going to go right to the edge of the 180, the bottom end of 160 meters. This thing is not necessarily set up to run at 160 meters, but we're showing you an overall cross section. At 160 meters, it's got a 1.5 SWR, which is perfectly acceptable. Now the SWR is a calculated ratio from reflect power. Okay, SWR isn't a real thing. It's not. It's a unit of measure, but it is a calculated unit of measure to help people understand reflected power more, a little bit easier. Not more. Help people be able to translate their reflected power easier into something that is more easily explained. Each one of these points on this graph, I mean, there's a million data points this thing's taken. Okay, from here to here. That's an incredibly large span of frequency. It's producing like 250 milliwatts or whatever worth of output energy. And it's going, okay, so what's the resistance here, 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 but doing that like a million times across this chart. You see how that's presenting that to us in a standing wave ratio. So our overall ratio of frequency and what our reflected power is, or our standing wave, our return wave, our resistance wave across frequency. That's what SWR is. It's a calculated mathematical term to represent your forward pitch of RF power versus your return RF power. Okay, so it's telling us that we want a little bit more induction. Just a scooch more. So I'm going to do another little trick here. I'm going to add another device to this thing. We're going to dial it in perfectly, and then we're going to find out what that is. We're going to pull it out, we're going to measure it, and then we're going to install it. So we're going to leave this graph static. We're going to hit stop. So that's where we're at. Let's see if we can dial this down perfectly, even though this is well within acceptable range. So we pulled the 30 puffer out, replaced it with a 50. Now, you don't need this big fancy piece of equipment that I've got. I've just been lucky enough that, you know, DeSpace was cool. When I called them, I spent a little bit of time talking with them on the phone. It was a little bit tough because they speak only Chinese, but through translating a couple other things, we were able to get figured out what I needed to have going on. But this unit gives me a lot of data, and I needed this for a completely different project when I was working on the MOSFET thing. This allows me to do circuitry emulation, so I could set this device up so that I can feed, let's say, this side of the transistor without the transistor in place, shunt load this side of the circuitry to ground to emulate a transistor with couplants of capacitance and resistance to ground, and then load this with a little bit of RF, hook up my coax connector to the outgoing coax connector and close this relay, and then look at the whole circuit all the way out to here and be able to make all the different adjustments and I want it with this particular unit. But I got so accustomed to using this, I sold all of my grid dip stuff, like my MFJs and my KC901s and that kind of, or not KC901, but my like AA30s and the stuff made by Rig Expert. They make a decent meter. Those guys really do. And really what we're doing here is we're using a grid dip function in this, but this has also got a Smith chart in it, signal generator, a tone generator, trace circuit ability, freak counters. There's like 70,000 pieces of equipment. There's 12 pieces of equipment in this little handheld device. And if you know how to run all of them, it's like opening your eyes and seeing the very first time you've seen a real 4K TV. You know what I mean? Ooh, shiny pretty. But when you guys go and check this downline, you don't need this big fancy piece of equipment. You just need something that's going to show you a frequency reference. Most of the newer MFJs now offer this because Rig Expert was pushing them out of the market and they had to step their game up finally for the first time in 30 years. The Rig Experts, I think everything from the AA30 forward allows you to have this ability. I even think the AA30, which is their base model, allows you to have this basic function. But the unit was telling me I needed a slight more induction before coupling to ground, so I gave it a little bit more longer of a leg here, shorten up the leg going to ground, and I increased my capacitance reference. And what we've achieved across from 3.4 megahertz to 30 megahertz, almost a completely flat response. So if we were to zoom in on this, let's see, span, let's say, oh, I don't know, 30. If we zoom in on this, so now we're looking at 30 megahertz wide, roughly. We're looking at 12 megahertz. Oh, come on. And all the way out and even further into 40 megahertz. A completely flat response of 1.0 to 1.1 pass through. So by us tuning this gentleman's ability to be able to hear and have RF pass in one side of the box and out the other, in the receive side and in transmit, brother, you can hear again, is the long and the short of it. Okay, so we've got our ICOM 7300, our 50 watt slug and reverse between a little Worthmore 2-pill, and over here on the peak output we've got a 1000 watt slug and peak, 500 watt slug and reverse, or 1000 watt slug in average, and a 5 watt slug and reverse. Now we're not going to pay too close attention to that because as we can see that slug is 2 through 30 megahertz, but the rest of these are 25 through 60 megahertz, and the rest of these are 2 through 30. 2 through 30. So let's take our camera and we're going to load it onto our tripod here, and we're going to let that be static. Now we're going to reach over here, we're going to turn the amplifier off. Okay, we are at 100% power output on the ICOM. This is in reflect, by the way. Hello. So what we're showing you is that pass-through tune. Remember what we just got learning about in the last couple segments? We're looking at the amount of power going forward, which is electrically traveling forward, out to the dumbing load. Hello. About 50 watts average, what the radio is supposed to produce. And in reflected power, coming back from the dumbing load and all the other meters and passing through the amplifier, hello, not even a watt. That's what we were shooting for. So, with 50 watts in average, all the way across, this is what we got. Hello, about 380 watts peak over here, 200 average, give or take a little bit, and look at the input tune. Hello, ridiculously low, just a couple watts. Now, because of the big attenuator circuit that's on the input of this amplifier, we're not going to see that input tune change an awful lot. But we have to have this here to prove to everybody in video land that we're actually putting the same quantity of RF into the amplifier. Now, The circuitry is going to change. There's going to be small fluctuations in the circuitry. Oh, it's telling me I got 4 minutes to record. Hold on a minute. Let me clear out the memory card. Okay. Hi, beautiful.
Hi, handsome.
What are you doing? I'm shooting a video for all the boys here.
Oh, sorry.
Say hi to everybody.
Hi, guys.
I'll come in just a minute, baby.
All right, love you.
All right, just give me a couple minutes. Okay, yeah, so, all right. As we go across the frequency response of this amplifier, the circuitry is going to represent to us slightly different points of resonance. Now, the way they set the circuitry up inside the worthmore is that it has pretty much got a flat response to it across the entire spectrum, just like what we were looking on the grid dip. That's kind of what we're going to get to, but we might stumble across a couple where this thing puts out a little bit more, a little bit less. It depends on what the transistor is seeing in the circuitry. When we go and we alter the circuitry, we're not tuning the device, we're tuning the circuitry to the device. So the device is going to operate flatly. And as we go across the frequency, there's going to be little points where it's going to be more resonant and less resonant. So where we're going with that, so let me start over. Got to revalidate my data. Let's put that 50 watt slug in a forward position. 50 watt element. The 50 watt slug in a forward position. Hello. Got 50 watts going in. In reflect. Hello. Nothing. We're seeing about 300 average. Hello. Just a little bit more on the peak meter. Remember, we're metering all of this in sideband. So the average and peak numbers should be fairly close as we go across the frequency response. Hello. Hello. Oh, wait a minute. We're out of band. Oh, that's right. I lied. Okay, here. Hello. Classic case. Look at our peak meter over here. Hello. So you lost about 25 watts, and that has to do with the circuitry inside the box. Remember, the frequency that we're wanting this thing to respond to is vast. That's a huge frequency difference between 80 meters and here. 80 meters in here. So, we're going to show you something. Hello. The same amount of input power. Hello. Same amount of output power, or the same amount of input reflect. Hello. A little bit less on the average meter. Hello. A little bit less on the peak. That's okay. It's normal operation. Without having a bandpass filtration network in here, or another way to put it, without having a notch filter network in place that is going to drastically change how the amplifier sees the in and the output of its universe that it's living in, its input network and output network. It's really hard to maintain that constant flow. But to see a 20 watt dip, I mean, literally that's what we're talking about, 20, 25 watt dip across the huge frequency spans. Brother, I can live with that. And I think everybody else out there can too. That's why the Worthmores are so popular. They're actually a very well built box for what they were at the time when they were made. Hello. Same thing. Hello. Same amount of input power. Hello. Hello. Now, in a real world test, I'd want to be interjecting, not through a microphone, but directly interjecting into this thing, 1,000 hertz tone. Okay? I don't believe in that. Do you talk in 1,000 hertz tone? Yeah, there's a couple parts of my voice that could hit into the 1,000 hertz range. But most of us, you, me, the dog, the cat, the neighbor, the kitten on the corner, we don't use 1,000 hertz tone in our voice, but they use 1,000 hertz tone as a standard. So if you inject X amount of millivolts worth of 1,000 hertz tone into X radio, you're going to get X amount of output power, and that's going to has to make everything universally flat. But the way we're testing it here is we're just showing that the thing is working across all the frequency response. Hello. Make sure our output power is at max. It is. Let's stop here at 10 meters. Hello. Hello. Point's proven. Amplifier works. Works all the way across the whole band without any massive tuning or anything. Now, everybody's gonna be like, oh, it's a splatter box. Touch my nipples. Look. See, how do I do this on video? I know, I have that device handy and in line and ready to rock and roll at all times. You'll find that most of your side harmonics that are created usually come from the radio or a pre-existing source before the amplifier device. So when I hear people say to me, oh, it's a splatter box, I'm like, yep, you're not knowing too well much of what you are talking about. So let's go take a look here. Let's go zoom in here. Okay, so let's do span. Boost our span up to 50 megahertz. So all the way out here is 0, and all the way here is 54 megahertz. Straight through the entire band. We're going to change our mode of operation to just AM. Okay, it's 10 meters. Do, do, do. Do, do, do. Do, do, do. It's the heat of the transistors working. We're sitting in 76 degree air. So we're picking up a couple degrees. Transistors themselves are about 116 degrees. Put attenuators nice and cool. It's the advantage of having this big old heat sink on this thing. So your amateur radio operator is pretty long on the microphone for the most part when you listen to them. I sit there and I listen every once in a while. And them guys like to talk. They really do. And back to the group, Ken. You know. So we've got to build for a heavier duty cycle. If you guys haven't figured it out, we're in transmission mode. We're doing a 60 watt carrier right now. It's pulling about 18 amps. As we can see, it's a 100 watt element, by the way. That's what it looks like on the 1000 watt element. And we're going to let this thing heat soak. I went and I installed this 120 millimeter fan. I put it directly over the top of the two transistors. Now the fan is held in there by rubber. And what I do is I take a piece of rubber and I sandwich it down inside the heatsink. So when you insert the screw into the rubber, it expands and it grabs onto the heatsink fin. That thing's on there, okay? But in the same breath, I want to make it so that the guy can take the dang fan off if he wants to, or change it if it quits, without drilling any holes into anything. It's something that we come up with about a jillion years ago. Had a friend show it to me way back when. We're at 86 degrees. So the whole point behind this test is to have the customer have some confidence in what he's got, really, more than anything. I know this is going to work. You know this is going to work. Let's zoom on down here for a minute. So we're doing a deep heat soak into this thing. See it? The filters always adjust. There's a lot of detail inside that little FLIR. So the picture quality is not this thing, the camera. The blue chart on it's a little off. So we're just going to let it heat soak for a few minutes, which we've been doing here. Now the only thing we got left to do at this point is to put the lid on it, which is just 4 screws. And we're done. I like these little worthmores. They're a great little designed amplifier. They run wonderfully. And we're not even over 90 degrees yet. And as you can tell, that fan's relatively quiet. It's not like we need to move a high volume of air. We're not pressurizing an enclosure and having it wrap around a bunch of components and, you know, then blow exhaust out through tiny little slits in the back of an enclosed cabinet. So we don't need a lot of back pressure, but this thing's moving a significant amount of volume of air out both sides. I mean, we're up to 91, 89 degrees is where we're sitting. 90. Now, the digital thermometer that's on this is an infrared thermometer, but then the camera technology itself is actually FLIR, but the temperature is not derived from the FLIR, it's derived from a digital thermometer that runs off of infrared signal. Call that person back. So when you shine an infrared signal at anything reflective, of course a little bit of the data gets lost, it gets bounced away because it's light. Reflective surface does what? It reflects. It's amazing. I'm just sitting here wondering how long we need to actually keep this in transmit mode. The things that worry me about these little worthmores is the bias resistors that are in them. So that's at 160 degrees. The tops of the transistors are at 130 degrees. That's at 140 degrees. And what I'm talking about is the capacitors over the output transformer, secondary transformer. The input pad, some of those resistors are 120 degrees, but nothing to get excited about. It's a good working little worthmore. So what have we done in this video? Well, we repaired the pass-through, which was blown up. We changed the transistors, which we had one of those that was bad. We looked at it on a spectrum analyzer, nice and clean. So we've demonstrated to the customer that they have the ability to talk through, have the ability to listen through, and we have the ability to talk into, and we have the ability to drive out. To where everything is nice and perfectly in resonance, and it doesn't matter where we use it from 80 meters on up. Do not use this on 160. You will be sad with the results. I mean, I don't think you're going to hurt the transistor any, even though it's just right on the cusp of what it should be doing. Stay away from 160 meters with this thing. But then again, I'd love to see a 160 meter mobile. I know they exist. It's going to have big, long, donkey antenna on it. I know. Big, giant bug catcher on it. It's probably. Big, long antenna. Long frequency. Oh, yeah, the other thing that we did is we hydraulically crimped and soldered on your Anderson clip. Okay? Now what I am going to send back with it is the old fuse holder and fuse wire and stuff. I strongly suggest that if you're going to put a fuse in line, guys, and I've been saying this in the last couple videos, because the last couple boxes I've worked on have shown up here with fuses on them. So if you're going to put a fuse on the thing, you're going to put this all the way up the battery. Okay? And literally like that far from the battery. The closer you can put this fuse to the battery, the safer you're going to be. Don't put it in line at the amplifier. It's not going to do you any good. Shit. Heat sinks at 80. It's at 203. Output transformers at 160. The tops of the transistors are at 120, which is no big deal. The bias is 120. No problems. Smooth operation. If you think about it, this thing's in Arizona. That's nothing than sitting in a car. Even that 160 degrees, that's nothing more than sitting in a car with the windows up in Arizona. Now, I haven't been keeping track, but I think we've been on the key now for quite some time. Yeah, we're not modulating it. We're trying to do a slow sink into the heat, and I think that we've reached our apex where we're not going to get any more saturation. And I'm sorry, the little bench 2950 just can't put out any more to drive this up. Still pretty cool. God, I love me Worthmore. Good old school tech. Guys, I'm going to go. Appreciate y'all tuning in to check this out. Gentlemen, my name is BBI. And without a shadow of a doubt, I am the biggest mud duck in Idaho. Come check us out, www.bbiamps.com. You can find me on Facebook, Twitter, Snapchat. No, I don't do a whole lot of Snapchat. And Instagram, and right here on the YouTube Gargler. If you like what you've seen, click subscribe. Give me a thumbs up. It makes both of us feel better. Guys, I gotta go. Catch you later. Biggest mud duck in Idaho. See you. Bye.